Ladies and gentlemen, on the main stage in 10 minutes and not in your programs, we have an Apollo guidance computer simulation from the Apollo guidance computer restoration team doing a moon landing from orbit to surface. That will be starting in 10 minutes. Please make your way to the main stage. Thank you.
Hey everybody, I'm Mike Stewart from the Apollo Guidance Computer Restoration Group, here along with Carl Planch, who is also part of the group. We are over in booth 36 if you want to come talk to us after this demonstration. Over the past year or so, we have been working on restoring an original Apollo guidance computer to working order. Our Apollo guidance computer came out of the lunar module LTA-8, which was the first man-rated production lunar module, and it's completely working now. We got it working again. Unfortunately, we weren't able to bring our AGC here. There is an AGC here at the RR auction booth, if you want to check it out. What we have here instead is this gate-accurate FPGA replica of the Apollo guidance computer. So the digital section of the computer has been translated one-to-one into Verilog running in this. That's the blue half. The black half is the prototype version of the debugger board that we built for the real AGC. The demonstration that I'm going to be doing is using a space simulator called Orbiter, which is free. You can download it online, along with an open source plugin for Orbiter called NASSP, which stands for NASA's Apollo Spacecraft Simulation Program. NASSP implements the Apollo spacecraft down to a ridiculous level of detail. Most of the subsystems are modeled relay by relay. And normally it runs an emulator of the AGC. But I have modified it to, instead of using the emulator, talk to my debugger board so we can get inputs to the real AGC and out, or in this case, into the FPGA version and out. So I'm going to go ahead and plug my FPGA in. And we'll get started. Okay, it's working. So what I'm going to be flying is the Apollo 11 landing. We're running the same software that was flown on Apollo 11, Luminary 99 Revision 1. A gate-accurate FPGA replica running the real original software. We'll be flying from the descent orbit down to the surface. We're about 3 minutes away from power descent initiation when I start the scenario here. So let me get started. Okay, so the first thing that I have to do is start program 63. Program 63 is the landing program. It is specifically the braking phase, so this will take us out of orbit. So I'm going to do verb 37, enter, 63, enter. Verb 37 is start program. While that's thinking, I'm going to look over to the left and push in the landing radar circuit breaker to turn on my landing radar. And so the way you interact with the AGC is through verbs and nouns, as they called it. This is one of the very first real-time interactive computers. And the verb and noun concept is what they settled on for talking to it. So you can either do a thing or you can do a thing to a thing. And it's all numeric codes that you have to memorize what they mean. So noun 61 here is showing me how long my braking burn is going to be. So we're going to be firing our engine for 9 minutes and 50 seconds. This is the countdown. We have 2 minutes, 45 seconds until the engine ignites. And then the last line is the cross-range distance to the landing site, 0.4 nautical miles. That's, if we were to go in our trajectory in a straight line, the landing site would be 0.4 miles off to the side. So I'm going to hit proceed to confirm that. I'm going to hit enter to skip the final alignment of the inertial measurement unit. And now I'm going to set some switches to give the AGC control over these displays up here, which I'll talk about in a bit. And now on flashing verb 50, noun 18, I can hit proceed, and the AGC is going to maneuver the lunar module to the burn attitude. So this is the direction that the lunar module, the AGC wants the LEM to be facing when it turns on the engine. Enter to go past the screen, and now it's going to do a lot of calculation to figure out exactly where we're going to be at ignition minus 30 seconds. So while it's thinking, the displays that the AGC is controlling up here are these tape meters that'll show our altitude and altitude rate in feet and feet per second. It controls the error needles, these little lines on the side off of the attitude indicator that show how far away we are from where the AGC wants us to be pointing. And then the cross pointer, which shows our forward and lateral velocity, which is not useful now, but will be very useful late in the landing. So this should finish calculating soon. Okay, so now I have to do a workaround for a bug in the Apollo 11 software. I'm going to do verb 21, noun 01, enter. That's load single octal value into an address. I'm going to use address 110 and put 102 into it. That is the radar modes flag word register. It happened because the way I loaded the state into my FPGA replica, I had to cause the computer to restart, and when it restarted, it forgot where it put the landing radar. So I just corrected its idea of where the landing radar is. So at ignition minus 35 seconds, we're going to get a blank on the diski. And that is my cue to arm the descent engine. And now a routine called average G is running. Average G is what takes our accelerations and feeds them into our state vector, which is our position and velocity as we fire the engine. So our display right now, we have the countdown in the middle. The top line here is our surface relative velocity, 5,567 feet per second. I have an ullage burn going now to settle the fuel. Flashing verb 99, I hit proceed to allow it to start the engine. And now our engine is at 10% throttle. I'm going to set the descent engine command override switch to keep the engine on. And from now up until ignition plus 26 seconds, which you can see on the event timer here, we are at 10% throttle. At 26 seconds, we will throttle up to 97%. So there's throttle up. And so the display on the diski has changed to noun 63. Noun 63 still has the surface relative velocity in the top row. You can see it counting down since we're firing our engine now. The second row has changed to our altitude rate, so we are going down at 5.6 feet per second. And the last line is our altitude, 46,878 feet. You'll notice that I'm saying point here, 8.7 feet per second down. The astronauts had to memorize the location of the decimal point in every display because the display doesn't have any points in it. So that's an additional challenge to memorizing all the noun codes. So the altitude rate and altitude information being displayed in the last two lines of the diski here are also being displayed on the tape meters. The AGC is sending this information out to this display too. These tape meters are just, they're tapes with numbers printed on them, and they move up and down according to our current altitude on the left and altitude rate on the right. And these were added both for redundancy and because the astronauts who were pilots really liked the more analog way of seeing visually how their altitude is changing and how their altitude rate is changing. So the next event we have coming up is at ignition plus 3 minutes and 30 seconds. Right now, if we look out the window, we can see the lunar surface, and that's because we're flying in what's called heads down mode. Apollo 11 was the only mission that flew like this. Every other mission, they flew with the windows facing away from the surface, so the astronauts couldn't see the moon. They were flying like this on Apollo 11 because Neil Armstrong really wanted to try to recognize the landmarks as they were flying by, which ended up being really useful because Apollo 11 was quite a bit downrange from where they expected to be because they hadn't fully depressurized their docking port when they separated from the command module. But anyways, the problem with flying heads down like this, and the reason why the later missions didn't do it at all, is the landing radar, which tells us how high we are and how fast we're moving relative to the surface, is on the opposite side of the lunar module as the windows. And so as long as the astronauts can see the surface, the landing radar can't, which is fine this early in descent because we're too high for the radar to get a lock anyways. But as soon as we get about low enough for the landing radar to see the surface, we're going to want to roll the LEM over so that it can get a lock. So we're coming up on 3 minutes, 30 seconds here. I'm going to move my hand controller to the right to start doing the burn, to change our yaw. The AGC is what's in what's called minimum impulse mode right now, which means it fired a couple thrusters to get us turning like this, and now we're just spinning without any thrusters firing. But I have to keep my hand controller deflected to the side. As soon as I want to stop spinning, I'll let go of my hand controller, and it'll fire thrusters to stop me from spinning. So I'm just going to do a 180-degree spin here, and stop it as soon as we get to the double or the triple lines here on the attitude indicator. Okay, and now if I look down at my disky, the altitude light has gone off, which means that we've gotten a lock on the surface. So if I do verb 16, which is display 3 decimal values, noun 68, this display has in the bottom row here a very important number called the delta H. Delta H is the difference between how high the AGC thinks we are and how high the landing radar is saying we actually are. So what this is saying right now is that we are 4,000 feet lower than the AGC thinks, which is a problem for the landing, right? Because the computer's going to send us right into the surface at this rate. So what I'm going to do is verb 57 enter, and that allows the AGC to start using the measurements from the landing radar. And now if I do a verb 16 noun 68 enter, we'll see the delta H slowly count down as the AGC slowly incorporates the radar readings into its idea of where we are. So this should count down to within 10 feet or so. Okay, so we're looking good on altitude now. The next event that's coming up is ignition plus 6 minutes and 45 seconds. And that is when our descent engine should throttle down. The descent engine is not stable at throttle settings between 60% or so and 97%. So throughout this entire landing, we've been flying at 97% throttle. As soon as the guidance for the AGC wants less than about 67%, the throttle is going to snap down to that. It happens at a very predictable time during the landing, and it means, if it happens on time, it means that you're on a good trajectory. So we're going to just sit here and watch our throttle and make sure that goes down right at 6 minutes, 45 seconds. And there we go. Okay, so we're on a good trajectory, so that's good. Throttle down was on time. In the Apollo 11 transcript, there's an exclamation point there, the only one in the entire landing transcript, because they were having problems with the computer, which we'll get to in a bit. And seeing this throttle down on time meant that it was still taking them where they wanted to go. So next step on the checklist, I'm going to set the mode to attitude hold, the AGC mode to attitude hold. And in attitude hold, I can use my hand controller here and move the lunar module around as much as I want. The goal here is to test to make sure that all of my inputs are working. So it looks like my joystick is totally good. I'm going to flip back into auto mode, and the AGC is going to take us back to the direction it wants us to be pointing. So my inputs are good. We should be good for the landing. I am going to do now a verb 16 noun 68 again. This time we're looking at the middle row. The middle row of noun 68 is the time remaining in the braking phase. So it says 1 minute 23 seconds. It's a bit misleading because as soon as it counts down to 1 minute remaining, we're going to switch into the approach phase, program 64. That is at what's called the high gate. So at this point, the lunar module is going to pitch forward so we can see out the window where our landing site is for the first time. So there's program 64. If I look out the window, we can now see our landing site. So we are now looking at noun 64. The interesting number here is the top right, the most interesting number. This 59 is an angle, and if I look at the markings on the window, which is called the landing point designator, at that angle, so 57 degrees is right here, I can see where the AGC is trying to take me. And if I hit proceed on this screen, I can use my joystick, just quick deflections forward or to the sides to change the targeted landing site. So I press forward a couple of times, the lunar module is pitching forward, and now, according to the landing point designator, my landing site is going to be around here. So I can do that as much as I want. The number here is the number of seconds that I have remaining to make those designations, so I have quite a bit of time to do it. The second line, I got a program alarm, 1 second. Verb 05, noun 09, enter. So we got a 1202. So I'm going to ignore that alarm because Houston says we're go. So I'm looking also at the last two lines here. My altitude rate, we're going down at 35 feet per second. We are 1,100 feet above the lunar surface. There's another program alarm. We're 900 feet up. When we get to about 500 feet, I'm going to do what Neil Armstrong did and switch into manual mode to divert away from this boulder field that we're going into. So to do that, I'm going to switch into attitude hold, push forward, and click my rate of descent switches here up to null my descent rate. Okay, so we are now in a hover. So the way I did that, AGC and attitude hold, which again just gives me control. I can pitch the LEM around as I want. And then I have what are called rate of descent switches, ROD switches. Every time I press one of these two buttons that I have mapped to my joystick, the AGC slows my rate of descent by 1 foot per second or increases it by 1 foot per second. So in this mode, I'm controlling the attitude and through that my horizontal velocity, and the AGC is controlling my vertical rate to the number that I have set into the middle register here with my rate of descent switches. So we are just going to fly along forward here for a little bit until we get to a nicer area. I'm going to switch my cross pointer here into the low multiplier. So this is now showing me in feet per second what my horizontal and forward velocity are. When I have those zeroed and I'm at a stationary hover, the cross will be right in the middle. So this is what I'm controlling to. I'm going to look at that last alarm I got. Verb 05, noun 09, enter. So it was another 1202. The computer load is much less in program 66, the manual mode. So I'm not worried about getting another program alarm. So what I'm going to do now is, we've got about 6% fuel left. I'm going to pitch back and roll to the side a little bit to start nulling out my horizontals. The top row on the disky right now is my horizontal velocity, so 46.4 feet per second. Also going to start increasing my rate of descent. So we're going forward about 15 feet per second now. Rate of descent is 3 feet per second. Okay, so horizontals are essentially nulled out. Going down 5 feet per second. You can see my shadow coming in. The shadow was the most important factor in controlling the launch date for these missions, because they really wanted the shadow to be visible on the surface for the astronauts so they could gauge how high they were and how they were moving. So I'm going to now slow my rate of descent a little bit here. We are 70 feet above the surface. Our horizontal is less than a foot per second, so that looks good. 41 feet, we're starting to kick up some dust. Slow my rate of descent a little bit more. So we're going down 1.5. As soon as I see the blue contact light in the top next to the cross pointer, I'm going to hit the engine stop switch, move my hand controller out of detent, turn off descent engine command override, switch mode control to auto, and disarm the descent engine. And so now we are on the surface of the moon. So that's how you fly Apollo 11 landing. So at this point, Houston would make the stay or no stay call. They called it stay or no stay because go or no go is ambiguous as to whether you're going away from the moon or not. So stay or no stay. If I were to stay, I would do verb 37, enter 68, enter on the diski to switch into program 68. That would calculate my latitude and longitude and put us into surface mode. But that is sort of boring, so I'm going to do no stay. So I'm going to open up the abort stage cover and click this button. And the AGC commands separation of the stages, and we'll start taking us back to orbit. They made this as safe as possible. All I had to do was hit that one abort stage button. If you look at my other buttons here, you'll see this, the engine stop button is still pressed in, and I don't have the ascent engine armed. The lunar module is wired in such a way that it doesn't care. If I press in this abort stage button, it will get me back to orbit no matter what. And it'll go all the way back to orbit with no other inputs from me. So after that, the checklist steps say pull out the stop button, push in start button, and arm the ascent engine, but it's more of like a formality to make sure everything keeps working. So yeah, that was the landing. Anybody have any questions? Yeah. Abort will use the descent stage to get you back to orbit. So you'll press that if you're early enough in the descent that you still have enough fuel for the descent stage to take you there. It's a little bit less risky than doing a stage separation. Yes. Yes. So the way that I'm doing that is my debugger has the clock from the AGC going to it on the AGC's test connector. So I'm able to count clock cycles. And I also have an input to halt the AGC. So I have a little Verilog core in the debugger that counts clock cycles and periodically halts execution of the computer to more or less match the load that they were getting on Apollo 11. So those were real 1202s that we were seeing. There were four 1202s, one 1201. The first ones they got were in Noun 68. I didn't get those because they actually got a little bit lucky on Apollo 11 because Neil Armstrong had a policy against doing the redesignations in Program 64. The redesignations don't really work when you have enough overload to get the program alarms in P60 or in Noun 68. So I made the trade-off to get the alarms in Program 64, but still have it be functional for the demonstration. It was essentially shared up until Program 64, and then at that point, Neil would have been eyes on the landing point designator out the window, and Buzz would have been reading numbers off of the diski.
Repeat the questions.
Oh, sure. Any more questions? Yeah. Can I simulate docking with the command module? You can with this program, but I don't know how to do it. So I've only practiced the landings. But this simulator does the entire mission. Actually, the only way we know to set up scenarios like this, like in lunar orbit, is to fly the entire mission. So my friend Niklas Boig in Germany flew this entire mission for me up until the point where I started it. And he was using the emulator. So what we did is we just took the state of the emulator from that point in the mission and fed it into the hardware right when I loaded up the scenario, and then let the hardware take over for the emulator. More questions? Yeah. Yes, the AGC version of the FPGA is available on GitHub. It's part of the virtual AGC set of repositories. So if you go to github.com/virtualagc/AGC_simulation, that's the code that I'm running on this FPGA. Any more questions? Yeah. Yeah, so the 1202 error is, it's really the result of a really sinister integrations bug. It had been discovered by George Silver at the Cape while testing Lunar Module 3 and reported to Grumman, but Grumman didn't think it was important to fix it. And so the flight controllers didn't know about it, the astronauts didn't know about it. Essentially what it is the resolver that detects the angle of the landing radar was switched to a different reference voltage with a different voltage and different phase. And the difference in phase and voltage between what the analog to digital converter that the AGC was using and the reference voltage that was actually being put into the rendezvous radar made it think that the radar was seeking back and forth very quickly. And so it was generating a whole bunch of inputs to the AGC. And the way the AGC inputs work, it steals a cycle from the instructions to use the adder to add 1 or subtract 1 from the angle in hardware. And so this flood of +1 counts and -1 counts was stealing time away from the program that was executing. And it made, essentially, it backed up on jobs to do. The AGC works on a fixed 2-second guidance cycle. So once every 2 seconds, there's a job called the servicer starts that does all the guidance tasks. It figures out where you are, figures out how it wants to change the engine settings and reorient to get you there, and then it updates the displays. And so the servicer was taking longer than 2 seconds to finish. So once every 2 seconds, you'd get a new servicer, but the last one hadn't finished. So you were just stacking up these servicers, and then eventually you'd run out of spaces for new jobs, and the computer would restart to flush everything out. And you get a 1202 alarm when that happens. Good? Yeah, any last question? If not, you can see us at booth 36 over there. I'll be happy to talk more about this. All right, thank you.
Thank you so much.